Okay, let us continue. Okay. Okay, let's continue. So there is a question in the chat during the break. So can QDA come up with shared covariance matrices by itself, right? Like, so, well, it's possible, right? Like, so you start with QDA where you don't share any covariance matrices. Maybe just from the data, like you might learn separate covariance matrices, but they look very similar. It is possible, okay? However, you are having more parameters when you're doing QDA, okay? So that is what we are going to see now. So as a summary of what we have seen so far, right? So we are focusing on generative models for classification, right? Where the basic idea is to compute P of X given CK and P of CK, okay? And then use the base law to compute P of CK given X, right? So we looked at two algorithms. First is GDA, where you had this class conditional matrices having same covariance matrix or shared covariance matrix assumption. Then you had QDA, where they don't share the covariance matrix, okay? Now, let's try to compute the number of parameters that GDA and QDA has, okay? First of all, you have the means, right? So, like, if you have K classes, then you have K times M parameters for the mean, where M is the number of features, okay? Now, how many parameters do you need for the shared covariance matrix? Anybody? You have a M feature input. So how many parameters do you need for the shared covariance matrix? So covariance is like M cross M, right? So it's an M cross M matrix, like which talks about how different features covary. And we know that covariance is symmetric. So it's going to be M multiplied by M plus 1 by 2 parameters for the shared covariance matrix. Okay. And how many parameters do you need for the prior probability, P of CK? Let's say I have a 5-class problem. Okay. Now, how many probabilities are, like, how many parameters are needed for the prior probability of the classes? 4, right? So the fifth one is just 1 minus sum of the remaining. So you need K minus 1 parameters for P of CK. Is that right? So this is for GDA. Now let's talk about QDA. So QDA has same number of means, so it's K times M for the mean, right? Now you don't share your covariance matrices, which means there's going to be K different covariance matrices. So K times M into M plus 1 by 2 times for covariance matrices, and you have K minus 1 parameters for P of CK. Is that right? So QDA has much more parameters than GDA. Okay, so if you want less parameters, you should be using GDA. However, this assumption that covariance matrices are shared is a really very strong assumption. Okay, so maybe in the data set that you care about, it doesn't hold. Then it is just better to try QDA. Okay, but in general, it's also a good idea to try both GDA and QDA in your task. So you're doing model selection at the algorithm level, like whether this algorithm to use or this algorithm to use. Is that clear? Okay, now there is actually another way in which we can reduce the number of parameters that you're using in both these approaches, and hence have an algorithm which has lesser parameters but still nonlinear like QDA. Okay, so now that comes from like what we are going to discuss now, which is the naive Bayes assumption. Okay, so this is what the naive Bayes assumption is. The assumption is that the features are conditionally independent given the class label. Okay, Or in other words, the probability of X given Ck, right? So we talked about P of X given Ck in both GDA and QDA. Now this X is a m-dimensional variable, right? So that is why you have this m cross m covariance matrix. Now, this P of X1 to Xm given Ck, according to this naive Bayes assumption, these features are independent given Ck. So this is nothing but probability, the product of I is equal to 1 to m, P of Xi given Ck. Okay. Now, what would be the impact of this in the covariance matrix? So if I tell you I have m features, they are all independent. Now, how would the covariance matrix look like? Yeah.
For the covariance between pair of pairs will be 0.
Yeah, so it's going to be 0 for every pair except for the diagonal, right? Like it's going to be a diagonal matrix. So instead of having m into m plus 1 by 2 parameters, I just need m parameters, okay? Now, because of this assumption, okay, we are going to have a covariance matrix which is diagonal, okay? Now, this model, right? So, which has, so basically like when you take QDA, okay, and add this naive Bayes assumption, okay, so you will get a new algorithm which is Gaussian naive Bayes, GNB. Okay. Now, this is called a naive Bayes assumption because this is really a naive assumption, right? Like so, in reality, features are not going to be independent, right? Like so, different features will have a lot of complex interactions among themselves. So this equation seldom holds in practice, okay? So however, you will be surprised like that even though this is like a very non-realistic or unrealistic assumption, these models perform really well in most of the practical tasks, okay? So you will implement some version of naive Bayes in your assignments. So yeah, then you will see how powerful they are. Okay, so now, so what are the parameter requirements for Gaussian naive Bayes? It has km parameters for mean. It needs only km parameters for variance. No, there is no covariance anymore. There is just variance of each features p of xk, right? So then you need k minus 1 parameter for p of ck, right? So this requires lesser number of parameters than QDA, but it is still a nonlinear model like QDA, nonlinear decision boundary like QDA. Is that clear? Now you can take G and B and add shared covariance matrix assumption, okay? So then you are going to get even lesser parameters. You'll have only km for mean and just m for variance and k minus 1 for p of ck, right? So in general, like, so we have seen several variations of GDA, okay? So as a summary, there are two things you can play with, okay? So the first thing is like whether you are sharing the covariance matrix or not, okay? And the second thing is like whether you are using arbitrary matrices for covariance or diagonal matrix, okay? Now this arbitrary versus diagonal, right? So this comes from the naive Bayes assumption, okay? And this is for the covariance matrix. Okay, so now we can fill this, right? Like, so when you share covariance matrices and have arbitrary covariance matrices, so that is what our first algorithm was, GDA, right? Now, when you take GDA and not share covariance matrices, like what would you get here? QDA, right? So when you don't share your covariance matrices, you get QDA. Now, when you add the diagonal assumption, like the now naive Bayes assumption, you get Gaussian naive Bayes, okay? And this algorithm that we just mentioned in the in the end, right? It's called diagonal GDA. So the names really doesn't matter. So what matters is like like what are the different characteristics of these algorithms, okay? Now, depending on whether the covariance matrix is shared or not, you're going to have two classes of algorithms. This is the first class where covariance matrix is shared, which means you're going to get linear decision boundary. Okay, and this is the second class of algorithms where you don't share the covariance matrix, so you get nonlinear decision boundary. Okay, is that clear? So there is one answer in the chat for my previous question. Like, so when you have the naive Bayes assumption, you don't get an identity matrix, you get a diagonal matrix because there is still some variance with that particular feature, right? So, okay, so I think this summarizes our discussion on GDA. So any questions so far? Okay, so there is a question in the chat. Is GDA a generalized linear model? So GDA is a generalized linear model, but QDA is not. Okay, QDA is a nonlinear model. Any other questions? Okay, so far, I made one big assumption so far, which was not listed in my first two assumptions. Can someone guess what it is? So why did I start with P of x given Ck being Gaussian? So I made an implicit assumption there when I say P of x given Ck is Gaussian. Any guess? So what's the range of Gaussian distribution?
Like minus infinity to infinity?
Yeah, minus infinity to infinity. So in some sense, I kind of implicitly made this assumption that x is continuous, right? I made this assumption that the features are real values. Now, what if the features are not real values? Okay, so what if my features are discrete values, like 0, 1, or 0, 1, 2, 3 for that matter, right? Like so what if I have discrete features? Okay, then it doesn't make sense to have a Gaussian distribution to fit a discrete variable, right? Like Gaussian is for continuous variables. So now, maybe to make our discussion simpler, let's just talk about binary features. Like what if I have a feature xi which is just 0 or 1? Now, do I need to do binary? Like, do I need to do Gaussian here? Like, probably not, right? Like, so Gaussian is going to have the support over minus infinity to infinity. Like, on the other hand, this variable takes only 2 values. So I can do better by making an assumption based on some discrete distributions, right? Now, let's say there are m inputs features, okay, and they all are binary. Okay, now can you tell me, like, how would the general distribution look like? Like, if you have m features all binary, then how many possible configurations are there in this distribution? I have m binary features. So now I want to construct the distribution, like probability distribution, like like the probability distribution table. Okay, so now how many? Yeah, so how many configurations are there, right? So there are 2 power m numbers for each class actually. Okay, and how many variables should I estimate to fill this table? So for example, let's take two variables. Okay, let's just say I have x1 and x2, and they are both binary. So then my probability table will look something like this. So what is the probability for x1, x2 being 0, 0? What is the probability for 0, 1? What's the probability for 1, 0? What's the probability for 1, right? So this is discrete. It is not real values anymore. So you can talk about tables for probabilities instead of functions, right? So this probability table has 4 entries because of 2 power m, which is 2 power 2, right? Now, if you have 4 probability values, they all sum to 1, then you have 4 minus 1, 3 things to estimate. If you estimate these 3 things, the 4th one comes by itself, right? Like it's 1 minus sum of the rest. So you have 2 power m minus 1 independent variables to estimate. Okay, now imagine you have 100 features, 100 binary features. So how many variables are there now? It's 2 power 100. So you have to estimate 2 power 100 features from a small data set, right? Like, so that is never going to work out, right? Like, so when you have discrete setting, it is actually very difficult to construct this joint distribution of the features, okay? Now, this is where the naive-Bayes assumption is essential. If you want to come up with a practical algorithm for discrete setting, like you have to go with naive-Bayes assumption, because the advantage of naive-Bayes assumption is it is not considering the joint distributions. It is just considering the individual distributions, right? Like, so now let's revisit naive-Bayes assumption, but for discrete case, okay? So we have P of x given Ck, which is basically product over I is equal to 1 to capital M, P of xi given Ck. This is what naive-Bayes assumption is telling us, right? So now, if you start with general P of x given Ck, which is nothing but P of x1 to xm given Ck, there are m features, okay? Now, if I apply chain rule here, so this becomes P of x1 given Ck, P of x2 given Ck, x1, P of x3 given Ck, x1, x2, until P of xm given Ck, x1 to xm minus 1, right? Like this is just the application of chain rule. Now I can make the naive-Bayes assumption. By naive-Bayes assumption, I know that the second term, P of x2 given Ck x1 is just P of x2 given Ck, because I know x1 and x2 are independent given Ck. Similarly, I know x1, x2, and x3 are independent given Ck. So this becomes P of x3 given Ck, P of xm given Ck, or product y is equal to 1 to capital M, P of xi given Ck, right? So now I have m different binary random variables. So what kind of distribution can I use to model a binary random variable? I'm sure you would have seen a lot of distributions in the probability tutorial, right? So like what kind of distribution can I use for a binary random variable? Sorry? Binomial or Bernoulli, right? So we can use a Bernoulli here. So each probability of xi given Ck can be modeled as a Bernoulli, okay, with parameter mu k I. Okay, so the Bernoulli is going to have this parameter mu ki, which is basically the probability that xi is equal to 1 given Ck. Sorry, this is mu k1 or mu ki, whatever. Is that clear? Okay, so now we have a new probability distribution. Okay, so now we can repeat what we did in GDA. If you remember what we did in GDA, we had a Gaussian assumption. So we computed the log likelihood of the data based on the Gaussian class density, class conditional densities. And then we differentiated, set it to 0. We got the values of the distribution, right? So now first let's compute the likelihood. Okay, so now what is P of X given CK? So P of X given CK is basically the class conditional density based on the form of Bernoulli distribution. So we already know what is Bernoulli distribution's functional form. Like, so it's basically product over I is equal to 1 to capital M, mu ki of xi, 1 minus mu ki of 1 minus xi. Okay. Now this is very similar to what we have seen before, right? Like, so, like for example, when xi is equal to 1, then the probability is given by mu ki, because this thing disappears, right? Similarly, when xi is equal to 0, this disappears, so the probability is given by 1 minus mu k of I, right? Okay, now this is my P of X given CK. Now this requires how many parameters for a class? So previously we needed 2 power m minus 1 parameters, right? But how many parameters do you need to estimate now? Yeah? One parameter for one feature. So there are m features. So you only need m parameters. Okay. So now you can appreciate the power of naive Bayes assumption. In continuous random variables, it was not that much, right? Like, so from m square, we went to m. But in discrete random variables, from 2 power m, you go to m. Okay, so that's a big saving. And sometimes that is the only practical way to do GDA for discrete variables. Is that clear? Okay, so now let's consider the two-class problem. Okay, so we are interested in computing the likelihood. Okay, so probability of the data given mu1, mu2, and pi. Right? So for Bernoulli, you just need mu1 and mu2. For Gaussian, you needed mu1, mu2, and sigma, but here you just need mu1 and mu2. Okay, so now what would this be? So I'm going to skip a lot of steps and directly write the likelihood. Okay, now you should get comfortable with the likelihood. Like, so for new algorithms, like we will directly like the likelihood. But I'm going to explain how I'm writing it right now. Okay, so based on the IID assumption, which means things are independent and identically distributed. So if I want to compute the likelihood of the data set, it's going to be the product over all the examples. Okay. Now the likelihood equation, right? So it's going to be pi times product over I is equal to 1 to m mu 1i power xi of n 1 minus mu 1i power 1 minus xi of n. Okay, so this whole thing power t of n, and 1 minus pi times product over I is equal to 1 to capital M x2i xi of n minus 1 minus mu 2i. So this is mu 1 minus xi of n, the whole thing power 1 minus t of n. Okay, it looks like a really complex equation, but we can divide this out like so. So this is the prior probability for class 1. Okay, and this is P of X given CK with naive Bayes assumption, right? Similarly, this is the prior probability for class 2, and this is P of X given C2 with naive Bayes assumption. You get the product inside because of the naive Bayes assumption. Is it clear? Okay. Now to make things simpler, we are just going to call this whole thing as x and this whole thing as y. Okay. Now, what would be the ln p, right? Like, so it's easier to compute log likelihood than likelihood. So ln p of d given mu1, mu2 pi is given by summation over n is equal to 1 to capital N. Okay. Now, we're going to call this whole thing as x and y. Okay. So t of n ln x plus 1 minus t of n ln y. Is that clear? This is my log likelihood. Okay, so let us move this to the next page. Or maybe there's no use in moving. It's too big of an equation. So let's just keep it here and try to study this. Okay. Now this is what my log likelihood is. Now I just need to compute mu1i, mu2i, right? So if I compute mu1i, mu2 is going to be very similar. So we are just going to compute mu1i. Okay, so how would you do that? You differentiate this with respect to mu1i, set it to 0, you get your answer. So we are interested in dou ln p divided by dou mu1i. Is that clear? So this is going to be dou by dou mu1i of, so mu1i exists only in this term, right? Like not in the second term. So you can ignore the second term. So it is just the first term. So it becomes Tn, okay, times, okay, but there is also summation. So I should add the summation. So it's basically summation over n is equal to 1 to capital N, Tn ln mu1i of xin multiplied by 1 minus mu1i of 1 minus xin. Fine. So this I can simplify. So it's dou by dou mu1i of summation over n is equal to 1 to capital N. Okay. So there is t of n ln ab. Okay. So this is ln a, and this is ln b, right? Like so. So if I just take ln a, which is ln mu power x, it becomes x ln mu. Okay. So this term becomes x ln mu I, okay, plus you have the second term, which is 1 minus x ln 1 minus mu1i. Okay, you also need the t of n here. Is it clear? Okay, so now let us just take this to the next page. We will differentiate this, and we have our, okay, I'm not able to cut this. Okay, so copy. Okay, this is what we have, and we want to differentiate and set it to 0. Okay, so summation over n is equal to 1 to capital N. So differentiate the first term. So you have t of n, x I of n. You differentiate ln mu, you get 1 over mu, right? So 1 over mu 1i plus t of n, 1 minus xi of n. You differentiate the ln x, you get again 1 by 1 minus mu 1 of I, and there is also minus 1. The whole thing is equal to 0, right? So now I can just multiply and bring the fractions together. So this becomes summation over n is equal to 1 to capital N. T of n, x I of n multiplied by 1 minus mu 1i, okay, minus t of n 1 minus, sorry, 1 minus xi of n multiplied by mu 1i, the whole thing is equal to 0. So the denominator goes away. Okay. Now I can do a little bit of, like I can just bring the things inside from the product. So this becomes summation over n is equal to 1 to capital N. Okay. So T of n xi of n, okay, minus T of n xi of n mu 1i minus T of n mu 1i plus T of n xi of n mu 1i is equal to 0. So now you can cancel these two things. So it becomes much simpler. Summation over n is equal to 1 to capital N, T of n mu 1i is equal to summation over n is equal to 1 to capital N, T of n xi of n. Okay, or mu 1i, the probability for the feature 1 being 0, like the feature 1 being 1 for class, for this particular class, right? Like it's given by summation n is equal to 1 to capital N T of n xi of n divided by summation n is equal to 1 to capital N T of n. That's it. Okay. What looked like a really complex derivation gave us a very simple answer. So in this case, we are considering class 1. Okay, so for class 1, for feature 1, what is the probability for that feature being 1? I know there's a lot of 1 here. So for class 1, for feature 1, what is the probability for that feature being 1? Okay. Now if you look at the right-hand side, it basically takes an average or computes the frequency of this feature being 1. Okay, so mu 1i, if I have to write it in literal terms, is basically number of examples where xi is equal to 1 and t is equal to 1 divided by number of examples where t is equal to 1. You take all the examples where class is 1, okay, you count how many times that feature was 1. So that counting is what your mu 1i is. Similarly, we can compute mu 2i, which is for class 2, right? Is that clear? So in general, if you have to implement this algorithm, all you have to do is, so first of all, this algorithm is called naive Bayes, just naive Bayes, okay, for discrete case. And if you have to implement this algorithm, all you have to do is just count the frequencies to set up these probabilities. Once you have these probabilities, you apply Bayes rule. Is that clear? Now, we considered binary cases, right? Like in binary cases, it so happens that the maximum likelihood solution is frequency of ones and frequency of zeros, right? But if you have a categorical random variable, like if your feature has k discrete entities, like 0, 1, 2, 3, 4, or like some other k different values, okay? So then you're going to get a categorical distribution, like which is relative frequency of different classes, okay? So in the end, the naive Bayes solution is really simple. It is like counting things and setting up the probabilities, okay? So any questions? We are going to see an example application now. Before there are any questions? Okay, so let us look at an example application. Okay, so as an example, we are going to see how to do text classification using naive Bayes. Okay, now, so what is the task here? The task is given a document, okay, which is basically a collection of words. I'm interested in classifying this document into one of the k topics. Okay, so given the document, I want you to classify it to one of the k topics. It could include things like politics, sports, and so on. Okay, I have a bunch of topics. Given a document, I want you to classify this into one of the one of the topics. Okay. Now, first of all, you are giving me a document which is a collection of words, right? Like, and we know that most of these machine learning algorithms requires numerical input, right? Like not textual inputs. So the first question is like, how do I convert the document into some vector so that I can pass this as input features to my naive-Bayes algorithm, right? Like, so now to do that, we are going to do a very simple transformation. Assume that there are m words in the vocabulary. Okay. If you have m words in the vocabulary, then each document can be represented by a m-dimensional vector. Okay. Just to give you an example, okay, let's say I have my vocabulary which has apple, hello, like tomorrow, how many are. Okay, let's say this is my vocabulary. Now, how many words are there? So you have 1, 2, 3, 4, 5, 6, right? I have 6 words in my vocabulary, which means I can take any document and represent it with 6-dimensional vector. Okay, so now let us say I have a document which says, hello, how are you? So there is no you here, so let me add you. Okay, 7 words. So hello, how are you? Okay, now I can take this document which is hello, how are you, and make it a vector. So is there an apple here? No. So the first feature is 0. Is there a hello? Yes. So the second feature is 1. Now is there tomorrow? No. Is there a how? Yes. Is there a many? No. Is there a are? Yes. Is there a you? Yes. Okay. I took this document, which was just a bunch of words. I converted it into this vector. Now you can do k-nearest neighbor or linear regression model or naive Bayes, like whatever you want to do with this. Okay. Now, similarly, let's say let's take another document, which is how many apple. It's a very silly document. So let's say I have a document which is how many apple. Now, how would that vector look like? So it's going to be 1, 0, 0, 1, 1, 0. Is that right? No, there are only 6. So 1, 0, 0, 1, 1, I think 0, 0. So does everyone get how I convert the document to numbers? Okay. So now my input is a m-dimensional vector, right? It is 1 if that word is present, if it is 0 if the word is not present. Now I can easily apply naive Bayes here. So probability of ck given x is given by probability of x given ck, p of ck, okay? Now this is product over I is equal to 1 to capital M, p of xi given ck, p of ck, right? We know how to compute p of ck. You just compute the frequency. Similarly, you compute the frequency for all these things, and then you have your answer. Is it right? Now, will there be any issues if I apply naive Bayes for this document classification problem? So think about it. Like, let's say there are, this was a toy example, right? In reality, you don't have 6 words. Like, you might have like 100,000 words in your data set, okay? So you have 100,000 words, and let's say you're working on 5-class problem, okay? Now, you have to compute all these p of xi given ck, probability of seeing a word given a class, okay? Now, will there be any issues that you foresee in this approach? Yeah?
The vector will be too big because
the vector will be too big. It's going to be 100,000 dimensional vector, but that is okay because you have naive Bayes assumption, right? Like, so, like you are not computing a joint distribution over 100,000.
And there will be probably a lot of 0 values.
So that is an issue, right? Like you might have a lot of 0 values. So, or the other way to look at this problem is if there are 100,000 words, there is not a lot of chance that you're going to see all the 100,000 words in all the topics, right? Like for example, let's take a word guitar. Okay, so now you might never see guitar in a sports document, in any of the sports document. Okay, you might rarely see. The probability of seeing it is not 0, right? So in reality, I can write a sports document which says, oh, the player knows how to play guitar. Okay, so then you have the word guitar there, right? Like so, but it is very rare that you're going to have such a sentence in the data set that you have in your hand, which means this product over M you have, right? This is product over 100,000 variables, okay? Now, almost always, some of them are going to be 0, okay? Now, isn't it bad? Like, so you have a product which has one of them or many of them being 0, which means the probability of CK given X is 0. So the whole model, for almost all the documents, you're going to get always 0 probability, because if you have 100,000 words, not all of them are going to be in the topic. So you will always have at least 1 0, which means the whole thing becomes a 0. Okay. Now, how would you avoid this? Okay. Before we talk about the solution, okay, this is the kind of practical problems you will see when you try applying the algorithms that you're learning in this course. Okay. So we are seeing one example here, but of course we cannot talk about all these kinds of problems in the class. That would require 2-year-long course, not a semester-long course. Okay, so but this is one example, like where we discussed an algorithm, we try to apply it in real world, it doesn't work easily. Okay, but this is not an uncommon example. Like every algorithm that you're going to try to apply in practical world, you will have some issues, and your job is to fix those issues. Like you cannot do things off the shelf like that easily. Okay, so now let's talk about this issue. So how would you avoid this issue? In fact, you're going to do this in your assignment as well. Well, maybe I should have given this without telling in the class how to avoid this issue, but then based on today's feedback, it's better we discuss this, yeah?
Using logarithms?
Using what?
Logarithms.
Would using log fix this issue though? So if you use log here, you are adding, so you can just ignore the 0 evens, but that creates additional issues. So what is that? Yeah.
You would have a logarithm of 0, so it's undefined.
Yeah, but log of 0 is undefined. You can ignore it, right? Like you can just consider log 0 is equal. There are many places where you will just treat these undefined values as 0. Okay, so you can consider log 0 to be 0. You just ignore those terms in the sum, but that is not a great solution. Why? So do you guys understand the solution? The solution is the issue is mostly because of the product, right? So instead of product, if I have log, if I take log, then I have sum of 100,000 things. If some of them are log of 0, I can ignore them. Okay, but is that an optimal solution, right? But it's one step ahead, like it's a good practical solution, but there's a catch there. The catch is now you are talking about like not so well-defined probabilities, because one computation is probabilities over, like for example, there are 5 classes, okay? For you to compare the probabilities, like you should have similar random variables, right? Like, so if you ignore some random variables in one probability computation and ignore some other in another probability computation, you don't have like a valid, you might not get a valid probability distribution. So in other words, you might have wrong answers, okay? Now, there's actually an easier way to avoid this, okay? So which is the idea of smoothing, okay? So the standard smoothing that people do is Laplace smoothing, okay? Which is basically the simplest possible way to get rid of 0. Okay, we are going to make an assumption that imaginatively, okay, in imagination, we have seen all the words once. Okay, so the counts don't start with 0, the counts start with 1, which means you get very low probability. then you have to use log. Okay, so if you don't use log, well, first of all, you have to use log here. Like product will not work. Okay, so product is in theory okay, but like when you compute product of 10 different probabilities, you're going to have numerical imprecisions. So you have to use log. Okay, now the Laplace smooth, the idea of Laplace smoothing is mu1i is equal to number of examples where xi is equal to 1 and t is equal to 1 divided by, so this is what the number of examples where ti is equal to 1. So this is what my previous estimate was, right? Like I'm just going to add +1 here and +2 here. Okay, which means for both the classes, like I'm adding 1, 1. So the probability of seeing class, I would imagine that I have seen the value 1 once and value 0 once already. Okay, now if I have no examples from a class, then this term is 0, this term is also 0, right? So then I get the probability of 1/2. Is it right? So I can, if I have not seen any examples from a class, I assume that the probability of seeing the word is equal chance, like 50-50. Instead of assuming it to be 0, which is a really bad assumption, we're going to make 50-50, okay? Now, is this a correct assumption to make? Is this correct to say that the probability of seeing guitar in a sports document is 0.5? No, right? But practically we have to do it like to make things easier. So in other words, like what we are doing here is like we are really introducing our own bias to the model, okay? So this prior probability that mu1i is equal to 1/2, right? So this is a bias, okay? But sometimes these kind of biases are needed for you to start learning. Now the good thing about this bias is this bias is going to slowly disappear as you see more and more data, okay? For example, if all examples have xi is equal to 1, okay? There is this one feature which is always 1 in a particular class. Okay, for example, let's take game. Okay, the word game in sports. Okay, almost always you see the word game in all the sports document. Okay, however, when you started with 0.5 probability. Okay, now what happens to p of xi is equal to 0 given class 1? So how many times you have seen 0? You have not seen 0 at all. You're always seeing 1, but there is this imaginative 1, so you just put a 1 here, divided by the number of examples where t is equal to 1 plus 2, right? So initially it is going to be 1/2. After you see the first example, it is going to become 1/3. Then it is going to become 1/4. Then it is going to become 1/5, right? After you see 1,000 examples, it's going to become 1/1000 or 1002, whatever. Okay. Now, this just means that the probability goes close to 0 after seeing lots and lots of examples. So we have a bias here, but it is not a really bad bias because, like, as you get more and more data, you can update your prior with the data. Okay, is that clear? So probably we will stop here since we are out of time, but just to give you a very, but today we saw a whole family of algorithms, okay? So we had discrete features and continuous features. In the case of continuous features, like we looked at GDA, QDA, GNB, and diagonal GDA, right? So we saw a family of algorithms which can be used with Gaussian assumption. Then for discrete features, this is with Gaussian assumption. Discrete features, we had the Bernoulli assumption, and we looked at naive Bayes, right? Or Gaussian naive. No, it's not. It's the Bernoulli naive Bayes, right? I think that concludes our discussion on generative models. Like so, next week is a break. Is it a holiday break or a study break? Okay. Okay, so it's a study break. So maybe it's a chance for you to revise the lecture notes and the assignment 2 will be released, so you can work on your assignment 2. So the next week after that, right, like, so we are going to talk about discriminative models and followed by discriminant based models. Okay, so so whatever we did today concludes our discussion on generative models for classification. So we will stop here. As usual, this is my office hours, but I see there are people already waiting for the next class. There's a class at 4 o'clock. Okay, so is that going to go till 7 o'clock? Okay. Anyways, like I'll take questions here, but if they kick us out, we'll go to my office.